Maria to give us a talk about exoALMA fab. Thank you, Richard.
All right, hi. I'm going to share my screen real quick and
get
started.
Please go.
Can you all see my screen?
Yes.
All right, awesome. Thank you all so much for inviting me to talk today. My name is Maria Galloway-Sprietsma, and I'm a fourth-year PhD student at the University of Florida working with Jaehan Bae. And today I'm really excited to talk to you about my work with exoALMA. I focused on the emission surfaces and temperature profiles of the 15 disks. I also just want to say a huge thank you to all of the exoALMA collaborators. None of this work could have happened without all these people listed here. So thank you to everyone there. So to get started, one of the fundamental questions we can ask about protoplanetary disks is, how is the gas distributed? This is a cartoon that I'm sure many of you are familiar with that shows the midplane of a protoplanetary disk where there's maybe some larger solids and some gas, and the atmosphere of the disk where the solids are smaller and there is more gas present. So understanding how the gas is distributed radially and vertically can give us actually a lot of insight into the physical characteristics of the disk. So this can tell us about the chemistry and substructures within the disk. So we can learn a lot about the dynamics from this. We can learn about the thermal structure, which I'm going to talk about today. This can give us insight into the kinematics, and understanding the emission surfaces is actually critical to doing a successful kinematic study, because you need to know the layer of the gas that you're studying. And this can help us uncover signs of planet formation, and is also critical to calculate the disk mass. And then finally, we can even learn about the disk environment by looking at these emission surfaces. So the great thing about exoALMA, as Rich explained, is that we targeted 3 different molecular tracers. And this is especially helpful because this can give us a 2D view of the disk, because different molecular tracers will allow us to see deeper into the disk. So we can get a good sense of the atmosphere all the way down to the midplane. So my work on exoALMA focuses on the emission surfaces, and that is what I will talk about today. So how do we actually obtain the emission surfaces? As Rich said, we kind of used 2 open source Python packages for a lot of the exoALMA analysis. One of those was Disk Miner, which Rich introduced. But today I'm going to focus more on the data products we obtained using DiskSurf, which is a code that Rich actually wrote himself. And the reason I'm focusing just on the DiskSurf products is because this methodology gives us the non-parametric surfaces, which capture surface substructure and is what we used for the temperature profiles. So just a quick overview of how DiskSurf works. DiskSurf looks at the individual channel maps for a disk, and it picks out peak points along isovelocity contours for both the front and back surfaces. So you can see that here with the front surfaces in blue and the back surfaces in red. So this is done for a selected amount of channels across the entire disk. And then this information is azimuthally averaged to give us something like this, which shows the height of the emission surface over the radius. And so this is kind of like a dirtier version of an emission surface that isn't cleaned up yet, but you can see here this flared front surface and a little bit of the flared back surface. So this is the methodology I'll be talking about today. And we did this for all 15 disks. This is for 12 CO, J equals 3 to 2. This is for 13 CO. And these are the surfaces we retrieved for CS. We don't have all 15 surfaces due to signal to noise constraints, but we were able to get them for these 6 disks. So when we look at this all together, we see something like this. This is a wealth of information, and it's been really exciting to dive into it. So some of the first things you might notice are there are these individual molecular layers. So 12CO sits above 13CO, which generally sits above the CS layers. There are some exceptions to this. In some cases, CS is really quite elevated, as in AA tau and SY cha. We also see that most of these surfaces exhibit tapered power law profiles, but again, there are exceptions to this. PDS66 is an exceptionally flat disk, and then CQ tau and MWC758 are also fairly flat. And then B4046 actually kind of has a double power law profile. And then one of the last things you might notice is that these surfaces are not smooth. There's actually a lot of substructure within them. There's gaps and bumps and some larger substructure that I'll talk about in a little bit. So again, I want to focus on the individual molecular layers. This is a really important component to a lot of this work because again, it allows us to get this 2D view of the disk from the atmosphere down to the midplane. And this is really helpful because we actually have the temperature data for each of these individual layers. So in this disk in particular, you can see these molecular layers are fairly clearly defined, and as we expect, the temperature varies vertically and radially. So this means that we can actually calculate a 2D temperature profile, which gives us a sense of how the temperature varies throughout the disk. And this has been done several times in work, first I think in 2003 by D'Artois, and in more recent works too, including for all of the MAPS sources. So we were able to achieve 2D temperature profiles for 9 of the exoALMA disks. And these disks are the ones that have well-defined molecular layers and high enough signal to noise within those layers to get a good sense of the temperature in each layer. You might notice that we are missing some information down at the midplane of these disks. And this is something that in the future I'd like to focus on, is really probing the midplane more accurately to get a temperature. So just some quick statistics about what we're seeing here. Of course, we see hotter atmospheric temperatures that range from 33 Kelvin to 67 Kelvin. The hottest disk is around a Herbig AE star, which makes sense. It's HD 34282. Although in this profile, it doesn't look like it is the hottest, but that's just because of this area over here. And then we see midplane temperatures of about 24 Kelvin, which is a little bit hotter than simulations suggest. So again, that's why I'm interested in better understanding the midplane of these disks in future work. And then the other data product that we produced for this paper were the radial temperature profiles. So how temperature varies as a function of radius. We have this here for all 15 disks, and these were calculated using GoFish, DiskSurf, and DiskMiner. So I'm not going to go over the comparison of all of those today. That's in my paper, but they're all quite consistent. And something you might notice again is that there is a lot of substructure within these temperature profiles. So we see some wiggles, particularly in alcalcium 15, SY cha, and AA tau. And some of them have like characteristic bumps and slopes that fall off. So these 3 data products represent the bulk of exoALMA 5. And I think the really exciting thing about these 3 is that while they're relatively simple, there's a huge amount of applications that they can be used for. So some of the things that Rich just talked about include a kinematic analysis and a calculation of the pressure profiles, which Joe Stadler did for his exoALMA project. And this included using the emission surfaces and the temperature profiles to do that more accurately. Cristiano Longarini used the temperature profiles and the emission surfaces to model the rotation curve, which allowed us to calculate the disk mass. And Giovanni Rosati used these results to interpret the emission heights and to try and understand why we see these layered emission layers. And I'm also really excited to see in the coming months and maybe years what other applications we can use with this data and what things we can learn. So one of the first things I want to talk about that we're seeing in this data is this large scale substructure. So I've highlighted the disks that exhibit this in red here. We can take a closer look. So these 4 disks all exhibit this diffuse emission at large radii. AA tau, you can see it here, has this very distinct morphology where we see this tapered power law emission surface, and then it sharply cuts off and we get to this more diffuse emission. This morphology is also mimicked in alcalcium-15, in 13CO, and in SY-CHA. And then DM tau has a slightly different morphology. This diffuse emission kind of just expands outward and doesn't really follow a tapered power law profile. And we have a lot of emission down at the midplane as well. These are the peak intensity maps and some selected channel maps where you can see this diffuse emission in the outer regions of the disk. I think it's particularly visible in the channel maps here, these outer regions. Hope you can see my mouse, excuse me, here and here. And in DM tau, this is, a slightly different morphology, but again, we have this really low signal to noise diffuse emission and no well-defined front or back surface. So to explain this, we invoked 2 scenarios. The first is projection effects. So are we seeing this morphology just because of the inclination of the disk? All of these disks are highly inclined, the ones that we see this diffuse emission in. And this is a model cube of a highly inclined disk where you can see the front surface here and then the back surface kind of showing through, particularly in the systemic velocity channel. We can see this back surface here. And then this is the real data of SY-CHA. And you can see that this actually really looks pretty similar to the model data for the highly inclined cube. Especially here, we can see this backside surface shining through. The other possibility that might be working in tangent with the projection effects is photodesorption. So Christoph Hint's 2018 paper on ion loop explored several different physical mechanisms to try and understand why the ion loop data looks like this. So it's very diffuse out here, kind of like we're seeing in these disks, and CO is not frozen out at the midplane. And they found that the thing that best explained these observations was a model that included ISM radiation and UV chemistry. However, 3 of these disks, AA tau, DM tau, and alcalcium-15, are actually located in Taurus, which has fairly low FUV radiation and is not really a star-forming region that we would expect to see photodesorption because there's not really any strong ionizing sources. So this work is kind of showing that perhaps large and radially extended disks are still being photodesorbed even in low FUV regions like Taurus. And this is interesting, kind of has implications for how disks differ throughout star-forming regions and how the star-forming region can have an impact even on the planet formation process because it's directly impacting the disk. So the next thing I want to talk about is some of the smaller scale substructure, which I'm just calling dips and bumps because that's what they are. I've highlighted them here in green in these emission surfaces, and you can see that they're pretty ubiquitous throughout all of these emission surfaces. We also see this substructure within the temperature radial profiles, as I've mentioned, and I have the dips highlighted here in dashed lines. So the first thing that we did was compare this substructure with the continuum substructure. So in these three plots, I am showing the continuum rings and gaps as dashed and solid lines. And then I'm also showing in pink and blue and orange the emission surfaces. So this is kind of a divergence from what the MAPS results found. We actually don't see a huge correlation between the continuum substructures and the gas substructures that I identified in the previous plot. The three exceptions to this are these three disks I've plotted here, AA tau, J1615, and MWC758. So in AA tau and J1615, we see that at the location of a gap, a continuum gap, we see this slope change in the CS surface in both of these. And then MWC758 actually has the, wait, let me close this. MWC758 actually has the clearest evidence of the substructures in the gas being related to the substructures in the continuum. You can see in 12CO and in 13CO, there is a pretty clear gap and slope change as the continuum fades out. So yeah, this is again a different result than MAPS, but this is potentially due to maybe some decreased gas surface density within transition disks. So AA tau and MWC758 are both transition disks. And this concept has been recently explored in a paper by Charles Law with PDS-70, the PDS-70 emission surface. So kind of zooming out away from where the continuum is, we are still seeing this substructure in the outer regions of the disk, in the gaseous portion of the disk. So a good example of this is calcium-15, where we see a pretty clear bump or pretty clear dip in this outer region. And then we also see two dips that are coincident between 12CO and CS, as well as a little bit 13CO. And a lot of the substructure is actually coincident with the temperature profile substructure as well. So this is a particularly interesting source because it's very wiggly, as you can see. Which maybe I'll like talk about it at a different time, the wiggles here. But these bump and dip substructures, particularly these first two, align with what we're seeing in the surface here. We also see this in 13CO and CS, particularly at 200 AU, there seems to be a pretty clear perturbation in the emission surface and temperature profile. So another really interesting thing about these substructures is that they often align with the kinematic signatures identified by Christoph Pint. So Rich talked about this a little bit, but in Christoph's paper, he looked at the channel maps of all 15 exoALMA sources and identified all of the velocity kinks. And in calcium-15, we see that one of the radial locations of the KPS is a little under 400 AU, which aligns really closely with this gap in the emission surface and with this bump in the temperature profiles. And this isn't the only source we see this. And actually every source with a kinematic planetary signature, we see a correlation between either the emission surface substructure and the KPS. So in J1615, we see a really clear bump in the temperature profiles at the location of the kinematic signature. In SY CHA, it's a little bit less clear, but we do see that the 13CO and CS surfaces cut off at the location of this velocity kink, and there is a slight dip in the temperature profiles here as well. AA tau exhibits the slope change in CS and a dip right at the location of this KPS in AA tau. And then J1842 has a dip in both emission surfaces within one beam size of the kink in the velocity channels. So this is an interesting result. I think it implies that the surfaces and the temperature profiles are somehow related to these kinematic signatures that we're seeing. And so we can potentially use these substructures to infer whether we're seeing changes in the density profile. And this is all potentially related to the planet formation process. So I'm hoping to work on this more in the future. So finally, I just want to talk a little bit about a comparison to the source properties. One of the great things about exoALMA is that we targeted 15 disks, which is a fairly substantial size, and it can allow us to do some statistics and compare to source properties. So before I go over these next slides, I just wanted to show this plot to kind of explain what Z over R is, which is what I'll be showing. So Z over R is just the average height over the radius of the emission surface. And I've plotted that here for 3 different molecular tracers in calcium 15. So Z over R is basically just this slope here. So one of the first things we did was to compare Z over R to the stellar mass and the average 12 CO temperature. These plots are compiled from data with data from Charles Law's works, so including the MAPS disks. And what we see is that mass and temperature don't actually have a really strong correlation with emission height. There's really not a correlation here at all. I've plotted mass to the -1/8 and brightness temperature to the -1/6, which are relations you might expect if you do some back of the napkin math with the gas pressure scale height. But again, there's no clear correlation here. However, when we plot Z over R versus the outer radius, so the outer CO radius, we see this really strong linear correlation, which has been seen in these previous works listed here. And this may be due to the disk flaring, driven by disk flaring, and it could also have something to do with the disk being puffed up. So larger disks may be more puffed up than smaller disks. We also explored the emission surface Z over R against disk mass. And here we find a pretty clear linear correlation. This is disk mass calculated via the rotation curve from Cristiano Longarini's paper, as well as some archival calculations. We also checked this relation between the disk mass and the dust mass. So these are dust masses derived from Pietro Curoni's paper for exoALMA. And we also checked this relation with disk mass derived via N2H+ from Leon Trapman's paper. And what we see in all 3 cases is a positive correlation between Z over R and the disk mass. And in particular here, we see a pretty clear linear relation. And this is actually predicted in Giovanni Rossotti's exoALMA paper, which tried to explain why the emission surfaces have the heights that they do. And in that paper, he finds that the emission surface positively correlates with the gas surface density, and hence it's related to the disk mass. So I think this is an exciting result and also a useful result because calculating the disk mass is not always straightforward. Sometimes you need the rotation curve or you need multiple molecular tracers to do some modeling. But here, if you have the emission surface Z over R, you can simply estimate it with this linear relation. This relation is also found in recent work by Teresa Peneque-Carreño's 2025 paper, who did some extensive modeling and found the same link between Z over R and disk mass. And she explains in that paper that this may be linked to the volatile carbon abundance of these disks. But I think it's really exciting that we're able to use the emission surface height to better understand the physical properties of these disks. And I'm excited to, in the future, kind of do some work more focused on these results. So see, I'm about 22 minutes in. but I'm just going to leave up my conclusion slide. So this work really focused on the emission surfaces, radial temperature profiles, and 2D temperature profiles to learn more about the exoALMA disks. Several of these disks potentially show evidence for photodesorption. All of these disks show some evidence of substructure, and this substructure is shown to be coincident between different molecular tracers, the peak intensity radial profiles, and the velocity substructures. And we find that the emission surface and disk mass are linearly correlated, and this offers like a straightforward way to calculate the disk mass. All right, thank you so much, everyone, for your time, and I'm happy to take any questions.
Thank you, Maria. Very nice talk. Does anyone have questions? Just use the raise hand function. Let me know. Does any questions? Yeah, in fact, I want to ask, in your research, what do you think about? Okay, maybe Josh Pican first. Yeah, please, Josh.
Okay.
Yeah, please.
Can you hear me?
Yes.
Okay.
Oh, can't hear you anymore.
Yeah, maybe I will ask. Yeah, I want to ask. In your research, do you compare your research with previous observations?
Yes. Yeah, definitely. So this work is really comparable to a lot of the work done by MAPS, which looked at 5 disks. And then there's also archival data of some of the exoALMA sources, which we also compared to. And our results are, I would say, in terms of the MAPS papers, we have pretty comparable results. We're finding, tapered power law, emission surfaces, similar temperature profiles. I would say that the areas that we differ from MAPS are, again, like the continuum substructures. So we don't really see a strong correlation between the continuum substructures and the larger, like azimuthally averaged gas structures. And then I think the thing about exoALMA that was really exciting was identifying the kinematic signatures. And so something that wasn't exactly done in MAPS was comparing the emission surface substructures to the kinematic substructures. So that's where we differ. And then in terms of the other archival data of these disks, we find really comparable results, I would say. The emission surfaces do differ slightly. So HT3428-2, L-calcium-15, DM tau, I believe those are the archival objects. We find that the emission surfaces differ slightly. And then the other big thing that we find is the sharp drop-off in the emission surfaces that potentially link to photodesorption. We don't see that in the previous works. So I think the high resolution of this data kind of allowed us to better see that morphology.
Okay, thank you. Just please go.
Okay, thank you. Yes, in fact, I want to congratulate Maria and Rick for these 2 exciting talks. My questions are more related to the fact if you are able to figure out how the particles, what is the size of the particles of this dust, and if there is evidence, will be the second question, of aging in some of the disk, thinking in the basic idea that a very young disk should be populated by micron-sized dust, while this dust could be aggregating into thicker particles for older